Hey guys, welcome to my channel. I'm back again with another really interesting video, and in this video guys we are going to discuss the quantization technique of large language models. So without taking any time further, let's get started. So first of all guys, you guys have been hearing a lot about quantization. So we are going to discuss what is quantization and what are the different techniques, and in the end we will also see simple coding Google Colab notebook on using one of the quantization technique to actually convert your model into a quantized model. Okay, but first of all guys, I want to refer you that this is the blog that I'll be using to actually explain these concepts to you. So this blog has been written by Maxime Lebon, who is a data scientist, and if you want to go through this blog on yourself, I'll be putting the link in the description below, so you can definitely refer it on your own time. So first of all guys, what is quantization? So guys, actually let's take this model, right? So you have got the new Google Gemma model and it says 7 billion, right? So Google Gemma 7 billion. So what is this 7 billion here? This 7 billion is the number of parameters this model was trained on. Okay, and if you think about it in this way, as the number of parameters increase in your large language model, your model becomes heavier and heavier, right? And their computational requirements also increase. So let's look into that. How do you use a model to predict anything, right? You first load the model using some libraries into your machine or into your Google Colab notebook, and then you call the generate method or predict method to predict the next step or the next text, right? But if you are loading that model on your machine, you are actually loading that entire 7 billion parameter database that model is trained on. And as these parameters will increase, you will need more memory to actually load those parameters on your machine. And I will use the word weights in terms of in place of parameters here, okay? Because what happens is that your large language model is basically the size of the number of parameters and the precision of the values of these parameters. And what is precision? Precision is a data type. So let's say your Gemma model is having 7 billion parameters, and each and every parameter is having the data type of float 32-bit. So just you have to multiply 7 billion into 32 to actually find out these are the total number of bits you need in your memory to load that model into your memory and then use it for prediction. Okay, so I can say that the 32-bit is basically the weight of your parameters. Okay, and for each and every parameter you are using this much bits, right? Now if you have that much memory in your machine, if you have 7 billion into 32-bit memory in your machine, great, you can use the model and you can use it. But most of us don't have that amount of memory, right? Some of you who are using a free Google Colab notebook know that you can only use a certain amount of memory, like 16 GB with a T4 free instance, and you cannot go more than that. So for users like us who just want to play around with this, it becomes really difficult to use these huge models for our own POCs. And then comes the important technique of quantization. So think of it in this way, that quantization is doing nothing but it is reducing or compressing the weights of your parameter, and by weights I mean the data type of your parameter, into a smaller precision value. So if your parameter was initially taking 32-bit to store itself, now it will only take 8-bit or a 8-bit integer to store itself. Okay, so basically you have reduced the size of your parameter by compressing it, and thereby you are actually compressing the size of your large language model as well, and then you can use it in a smaller machine or in a smaller configuration machine. Okay, now let's look at some of the techniques. So there are two major quantization techniques. One is post training and other is quantization aware training. So post training is nothing but guys that it basically means that you already have a pre-trained model. You already have a model like Google Gemma and you want to just quantize it, right? So you already have a fine-tuned model or a trained model, but you just want to compress it so you can use it on your machine. That's post-training. But if you have a model that you are fine-tuning also, or you are training it also, and side by side you want to quantize it in a smaller bit, then that becomes quantization aware training. Okay, that becomes quantization aware training. Okay, now this is the basic of quantization, guys. Okay, so you basically are converting a higher bit parameter size or a value into a smaller bit parameter size. Okay, and that's how you're reducing your model size. Now let's look into the some of the important quantization techniques, and one of the most popular quantization technique is GPTQ technique, but there is another technique called as GGML technique, which we will also get into but a little bit later. Okay, let's first look into the GPTQ technique. Okay, so GPTQ technique is also doing the same thing. Okay, and it is also converting your parameter into a smaller bit precision size. Okay, but GPTQ technique is actually very important or very useful if you have a GPU, but you have a GPU but with a lesser memory size. So for example, if you have a Huggingface, if you have a Google Colab and you have a T4 GPU with 16 GB of memory, then you can actually use the quantized model with GPTQ technique on that Colab repository to do your prediction or fine tuning or something like that. Okay, but if you don't have a GPU, then you cannot use the GPTQ technique for quantization. Okay, then you have to use a different technique, but we'll go into that later. Let's first understand what is GPTQ technique doing. So what GPTQ technique doing is that it is essentially taking into consideration a older technique which is called as the optimal brain quantization. And what does optimal brain quantization does? It basically does something called as creating new weights from the old weights, but compressing the weights such that the difference, the delta in the older weight and the newer compressed weight is minimum. Okay, so this is called as optimal brain quantization, where we are just trying to do a layer wise compression. Okay, and we are compressing the weight so that they are almost same as that of the older weight. Now what is layer wise quantization, layer wise compression doing? Okay, so for that we need to actually go into the transformers architecture. So let me click on this image here. So guys, your large language model is based upon these transformers architecture. Okay, and it's very important for you to understand, because what happens in a large language model is basically you take this input. So this is your input. Let's say you told your large language model that generate me a story of two children playing together in a park. So that generate a story of two children playing together in a park, that becomes your input. Okay, so when you give your input, then there is a encoding of that input that goes, and that encoding goes through multiple layers. So first is your embedding layer, where you basically convert your input into tokens. Then is your attention layer, where let's say your word is generate a story of two children playing in a park. So every single word in your sentence, through this attention mechanism, it is going to find out what is the relationship of every single word with every other word in the sentence. So let's say your word is two children. So two is your word and children is your word, right? So the relationship of two is significantly higher with the children word, because basically we want to say that two is the value of the children, right? So attention layer establishes the strongest relationship between all the words together by finding out by basically looking into the position of the word and also the semantics of the word, right? So once it knows how one word is related to another, we go into the feed forward network. Okay, and before that we go into a add and normalization layer, where we are taking the original input. You can see that we take the original input, which is not converted into the attention yet, and we just take this original input and we normalize it and we place it over to the output which is given to us by the attention layer. Why this normalization is done? So that we still keep track of the original input and we can match with the original input how much is our new attention layer created output, how much it matches with it. Okay, so we don't lose any information. And then we take that normalized input and we use a feed forward network, and feed forward is doing nothing but it is taking the input that you took, taking your attention input and your previous older input, and it is merging itself together, and it's basically creating another normalized output for us. So that's the input. Then comes the output. So now you know that this was my question. Now when you start generating the output, it also again goes into the same process where you have your output embedding, where again you will use a tokenizer that you will use later to convert your convert your tokens into words, because in decoding you will use vice versa, right? Now you will be generating tokens, but embedding you will use to convert those tokens into your normal output, like your text output, right? So you'll use your embedding, then you will use again those attention layers and those normalization layer and feed forward layers, and finally some softmax functions to actually generate the probabilities of output. These are the output probabilities, and then using those embeddings to actually convert those probabilities, probable outputs into the text formats, right? So finally you will get your correct output and you will predict it and you will generate the text, right? But you can see how much layering is present inside it, and at every single layer, guys, those 7 billion parameters of your GEMA layer are actually going through it. So every single layer has got those 7 billion parameters to be trained upon the upon your input, right? All those 7 billion parameters have their weights and values being computed. Okay, have their weights being computed basically means their values being computed, right? So when we know that at every single layer we have certain weights, right, that means at every single layer we have to compress those weights. At every single layer we have a compression problem, and that is the problem that optimal brain quantizer actually resolves. Okay, so if you look into optimal brain quantizer, that's what it is doing. It is taking each and every layer and it is trying to reduce the weight but make it as close as that to the original weight. Okay, but in case of GPTQ, it is taking the same concept but is applying 3 techniques to make that process much faster, because you know that every layer we have got many layers and we are compressing it every single layer, so the process becomes very long. GPTQ tries to make it faster by using 3 techniques. First is arbitrary order insights. So let's say you have this layer, right? And at every single layer you are trying to compress the output, compress the weight, right? Now what weight are you going to compress first? That was the order that you have to determine. But in case of GPTQ, we found with some research that you don't actually need to think about the order. So GPTQ doesn't think about the order and it just compresses all the weights in any order it seems to be fine. Okay, so in that way it can actually compress multiple weights in one single moment, right? Because it can simultaneously convert many weights together. It doesn't maintain any order. And because it is doing that, it can also do a lazy batch update. So let's say you have got 7 billion parameters and you are converting all these 7 billion parameters at once. It is definitely going to take much longer, right? But GPTQ doesn't do like that. It actually does a lazy batch update where it actually starts to transform all the weights in batches. So let's say it first transforms 10 weights, then 10 weights, and 10 weights. And because it does it in chunks, it actually is a much faster process, and also at every single block, it waits until entire block of weights is actually transformed and then only it goes to the next layer. Okay, but it transforms all the weights in chunks and not like all of them at once. And then finally, it also uses a clause key reformulation. So when you have such higher number of parameters, right, like 7 billion parameters, and you are doing a numerical calculation multiple times, the same calculation you are repeating it, there is a very high chance of a numerical error that is being populated, right? So if a numerical error comes and you are doing the same calculation and again, you might actually enhance that error a lot. So with Klossky reformulation, and without going into too much mathematical detail, it basically says is that it tries to remove that multiple calculation again and again, and thereby it makes sure that you have a more accuracy and less numerical error. So with these three techniques, guys, the GPTQ gives us much better results with quantized models than the original techniques. Okay, now how do you actually use code to quantize your model and actually load the model in your machine to actually use it, right? So for that, we'll go into the coding section. So this is the Google Colab notebook that I have, guys, and I'll go through it bit by bit. Now let's go into this. First of all, we are actually installing our library, which is AutoGPTQ. This is a library which we will use for quantizing. Then we have optimum.git, which is nothing but our model, Facebook optimum. Then we have got transformers.git, which is our transformers library. Then we have got a accelerate library because we are using a T4 GPU and we need that for our quantized model. So once you have all these installations done, you go and start doing the imports. So from transformers, we import the auto config, auto tokenizer, and GPTQ config. Okay. So actually you majorly just need auto tokenizer and GPTQ config. Not sure about auto config. I don't think you need it. But let's see how we are going to use these libraries now. So first is you take the model. So this is a model ID, right? Now you actually take the tokenizer of the model. Now just remember, guys, the first step in any transformer model is to get the embedding, right? So your tokenizer is the one which is going to give you the embedding. So you first load your pre-trained tokenizer, then you create your GPTQ config, right? So what your GPTQ config is doing, it is actually the config which is making sure that you give it the correct parameters to quantize. So what are the parameters? First is the bit. So let's say I want to quantize it to a 4-bit precision. Okay, then it becomes bits 4. Then what's the data set? So data set is basically a certain data set that you use to quantize your model, or basically tell your weights that this much you can compress and this much, how you are going to compress those weights, right? How you're going to train to compress your weights. This is the data set. So definitely I would say that you use a data set from the GPTQ paper, and one of the data set there is C4, but if you want to use your own data set, you can do that as well. But for me, because I'm still learning the basics of it, I'll just use the data set which is provided by GPTQ itself. Now the tokenizer, which is your pre-trained tokenizer, and then you just go to training your model or quantizing your model. For that, you load the model, auto model for casual LM, and then in this auto model from casual LM, we pass the model ID along with the quantization config, which is GPTQ config. And when you click run, you will see that it starts downloading the model and it starts quantizing the model layers. And in the end, you will have a model which is quantized with 4-bit precision with the help of GPTQ. And finally, guys, I have just used my Huggingface CLI login to actually push this model to Hub, and it actually has the model with me. So I'm just going to show that to you now. So if I go to my profile here, you will see, and that's my profile, see Super Lazy Coder. So if you go to my profile and you will click on this SLC Optimum 125 GPTQ, you will see that the model is loaded here. And you can click on this inference API, click on compute, and you can see that it will start computing some data. Obviously, guys, this model is very small, only 125 million parameters, and it's not going to be working very good. But if you use quantization technique or something like Gemma model or Llama model or something like that, see, some big models, you might see really good output on quantized models as well. Obviously, this one is not working that well, but it still generates the output, which is what we wanted to show you. Okay, so this is all about GPTQ technique, and remember, guys, this will only work if you have a GPU. So if you have a GPU but with a lesser memory, use the GPTQ technique. But we don't just want GPTQ, right? We want something that can run on our CPUs, and for that you need to quantize your models with the GGUF technique, or previously known as GGML technique. So what is that technique? Let's look into that. So first of all, guys, this is also a technique that is working on the same precedence that you are trying to compress the model weights, and just like GPTQ, right? But here the library that we are using for compressing the model is a bit different. So the library which is used for making the GGUF model or GGML model, basically previously it was known as GGML, but now it's known as GGUF. So the library that is used to quantize these models is called as a GGML library, and this is basically a C library. And this C library has a very high compatibility with another Python library which is called as LlamaCPP. Okay, so it has got a very high compatibility with this LlamaCPP library, and both are actually developed by Georgi Gargano. Okay, and it is written in C++, and this library can actually make sure that you can load your model on a CPU machine and run them. Okay, and this is the main difference between GPTQ and GGUF model, that with GPTQ you can only run on GPU, but with this you can actually run on CPU as well. Okay, and also the thing is that you can, so what happens in GPTQ model, that you can offload some layers of your model. So you have got multiple layers, right? You can actually offload some layers on the GPU, but with LlamaCPP also you can offload some layers to the GPU. So with LlamaCPP or with the GGUF models, you can still use the models on GPU as well and on CPU as well. Okay, and with GPTQ also, so as what it says, right, that the main difference was that with GPTQ you can run on a GPU, but with LlamaCPP also you can run on GPU, but you can offload some layers as well. So basically it's a little bit faster, right? And you can see that in this there are 35 layers for a 7 billion parameter model, and with LlamaCPP you are able to offload all those layers to a GPU, so you can run these models as well on a GPU and on a CPU as well. So I think this is much better. But now let's look into how you can quantize the the LLMs with GGML. Okay, so for that, guys, we have to look into a little bit of detail of the different type of GGML models that we can use. So if you go into this profile, the bloke who is also a really famous name in the LLM community. So the bloke profile has got a lot of models. You can see he has got these Mistral models and all these models, and he uploads all these quantized models in both GPTQ and GGUF format. And if you click on one of the GGUF files, you will see in the files and versions section that there are multiple variations of this GGUF model present. So which of the variations should you use, right? And why did they quantize with so many variations? So here's the thing, guys, that with GGML technique, actually the quantization depends upon the type of approach that you are using, type of model that you are using for quantization. And there are 14 different models that you can use for quantization. So start from Q2K until Q80, and here the pattern Q2K has basically Q, which stands for quantization, 2 which stands for the number of bits, and then underscore, and then K is basically some constant, right? So Q2K basically means that you are creating a model with a precision of 2 bits, and this model specifically, it has Q4K for the attention and the feed forward tensors, and Q2K for other tensors. Why is this difference, right? Because, guys, I told you in the transformers image that one of the most important layer is our attention layer, because this is the layer which is actually determining which word matches most with which word, right? This is the one which is setting up the relationship between your words, and the feed forward layer is the one which is actually uniting all your results together of all your attention layers, right? So obviously these two layers, attention layer and feed forward layers, are very, very important. So for these layers, you don't want to compromise on compressing your weights, compressing your parameter values so much that you lose a lot of value, right? You don't want that. So that's why for these important layers, you are storing them in a 4-bit quantization, whereas for all the other layers, you're storing the parameters in a 2-bit quantization. And if you go to the next layer, you can see that the attention and the feed forward layer quantization bits also increases, and the other tensors bit also increases. So if you see the last model, which is the 8-bit precision model, this model is going to be the heaviest model, whereas the first model was going to be the lightest model, but it is going to be the most inaccurate one. Okay, so when you are trying to quantize the GGML, you have these options, right? They have this trade-off of memory versus accuracy. So if you want higher accuracy, go with the last one. If you want lower accuracy but with lighter weight, you can go with the middle one, or depending upon your POC. But now let's look into how you can use LlamaCPP library to actually quantize your model. So unfortunately guys, I couldn't run this. I didn't have enough time to run it with a Google Colab. But I'm sure that you can all try to follow these steps and try it on yourselves. I'll try it myself too. And then I'll try to make a separate video on this as well, on just using LlamaCPP to actually quantize your models. But for now, let's just understand it theoretically. So the first step is to just clone the LlamaCPP library and just pull and clean your branch. And then you have got some libraries which are prerequisites to LlamaCPP installation that you just install. Okay. Then you take your model ID. Then you just do some installation of your LFS, and then you clone this model repository. So basically what you are doing is you first cloned the LlamaCPP library. Then you download the model on your system, right? And then here you are just saying that you are converting your model to a FP16 format, okay? Which basically you are trying to converting your model into a 16-bit GGML format, and that happens. And then you go to your quantization methods, where you are providing that I want Q4KM quantization and I want Q5KM quantization. And then for each and every quantization method, you are creating the model in the GGUF format. You're calling the quantize function. You're calling the FP16 Q type, and the method are all going to be here. So this is the Q type and the method is your Q4KM. Okay. So finally, when you are done with this, then both your models are created, and then you can just take this, you can just use each and every model which is present in your model list, or which is now present in your directory. So you can see that once the model is created, it's basically stored in your directory inside your root directory. There will be a model name / model name lower directory created, which will store your model in a GGUF format, right? So here we are just iterating through all the models that we now have stored in our directory, and then we are choosing to prompt those models with some prompt, like enter your prompt, and then whatever method that we are choosing. So for example, do we want to use the Q4K model or the Q5K model? But this is nothing, right? Once you have the model loaded, you can just choose any of the model provided the prompt that you have, and you can just ask it to do things for you. So here we are using the LlamaCPP library to first load the method. Okay, so load the method. This is the Q type. That's load the model, which is your Q type, the entire model. And then there is this n value here, which is basically saying the 128. I think this 128 value is something that I have to check, which I'm not sure about. But definitely these are some parameters that we are using. This NGL35 is basically the number of layers that you want to offload to GPU. So if you are using a GPU, you can use this parameter. If you are using a CPU, you can choose not to use it. And then finally you just set it the prompt, and then it is going to generate the response for you. But guys, if you think this is a bit too complicated, simply you can just do the steps until this point, right? And once you have the model in your directory, you can use a Python LlamaCPP library, right? So I can just Google it for you. So Python LlamaCPP, right? And if you just go into this llama.cpp docs in LangChain, you will see a lot of usage here. So you can easily follow this usage, and you can load your model using this LlamaCPP Python module, and then you can just call just like that, right? So here they are just taking a template, you're just calling the template, you're just using a llama model here, and they're just invoking the prompt and they're getting the answer, right? So if there are many ways to use the quantized model which are in GGUF format, and you can definitely just go until this step to quantize the model and then use the LlamaCPP Python library to actually use the model like this. Okay. But these are the ways, guys. These are the two most popular ways to actually quantize your model. First is your GGML approach, and second is your GPTQ approach. And I have tried my best to explain you guys how these approaches work. What is the advantage of one approach, and what is the advantage of the other approach? Why should you use GPTQ? Why should you use GGUF or GGML? I hope this video was clear to you guys. I'll try to make more videos on quantization as I progress my learning also in this. But by the time I think, but until then guys, I hope you guys like this video. If you did like it, please do not forget to like this video and share this video with your friend. If you have any questions, comments, suggestions, feedback for me, please do write down in the comment section below guys. And in the end, if you have not yet subscribed to my channel, please do subscribe and hit the bell icon for future notifications of more such programming and coding related videos. I'll see you guys in the next video guys. Until then, take care and bye bye.